Next up is Jim Posen from Irreducible, talking about binary proofs for Bitwise operations.
Thanks, Will.
Yeah.
Let me set my stopwatch here. Hey, everyone. Thanks for being here. I'm Jim. I'm going to talk to you about Binius64, which is the latest version of the Binius proof system that we've been working on. And I want to talk about basically the journey to get here, some of the learnings along the way. There were a lot of new ideas, but also a lot of discarded ideas. And it's ended up in this new proof system. So to start with the basics, what is Binius? Actually, not that easy of a question to answer. A lot of people think it's this paper that we published 2 years ago, which curiously does not have the word Binius in the name. And it turns out that that was a good thing that we didn't put it in the name, because we ended up taking some ideas but actually discarding many of them. So the core contribution to this paper was a polynomial commitment scheme for binary tower fields. And we shortly after this found a better polynomial commitment scheme, and actually Binius64 doesn't even use tower fields. Instead, Binius64 still uses binary fields, but it's a simple and standard degree 128 extension over GF2 that we ended up using. So instead of describing what is Binius by like the cryptography techniques that we use, I want to go to like why is Binius? Like what are the principles that we're trying to achieve with this system? So when we started profiling the existing ZK snarks that were out there, proving was very slow, and we set out to build a computationally efficient proof system, especially targeting custom hardware. As in, if we could build hardware specifically for ZK proving, which is what we were doing, what is the most computationally efficient? And we basically found these 3 bottlenecks. So the first is all proof systems just boil down to like lots of finite field operations, so you need to make your finite field arithmetic really fast. Now, it's well known that in custom hardware, binary fields are the most efficient. What not everyone does realize is actually on modern CPU processors, the fastest 128-bit cryptographically secure finite field available is the G-hash 128-bit finite field, because modern processors have acceleration for this. The second thing is we termed this phenomenon of embedding overhead, which basically all the proof systems suffered from. And in order to emulate bitwise operations, which are common like XOR and AND, you would pay the full cost of a finite field operation to do something on 1 bit of information. And this is really pronounced when proving classical hash functions, which is not a niche use case. It's of fundamental importance for backwards compatibility and security. So the way that most proof systems, including Binius v0, went about this is to throw a lot of arithmetization tools at the problem. So if you have too many gates, then we're going to make some custom gates. And to handle range checks, we'll add some lookup arguments. And then to handle control flow, we're going to build a virtual machine which can emulate program execution, and we'll use recursion for memory usage. But then each of these tools sort of creates more things that you need. So when you have custom gates, you're going to start doing like table layout planning, and the virtual machine needs a memory argument now, and you might want a custom language for that machine, which means you have a compiler. We have some precompiles, and now our tables are getting really wide. And when we have custom gates, now our verifier logic is getting dynamic, and it's maybe so dynamic that our recursion architecture needs to itself be a virtual machine in order to just handle recursion. And we sort of wound up in this tangled mess of complexity. And so Binius original v0 basically took all of these techniques and tried to throw everything at it, and some more that were specific to our settings. So we had this idea of we were going to arithmetize over multiple binary tower levels that our arithmetization had different data types. We wanted to leverage derived columns that were not committed, because if commitments are slow, then we can use these sum check-based reductions. And this sort of got too complex to handle. And so we wanted to change to building, okay, how do we make just a simple zero-knowledge proof of an identity credential, like a concrete use case that's not block proving, and all this stuff was getting in the way. And so we, for this client-side proving use case that we then wanted to tackle, kind of went back to the drawing board and said, okay, how do we make a much, much simpler proof system that's taking the advantages of what we have, but otherwise trying to be as simple as possible. And we arrived at Binius64. So we basically kept these four crucial components. So the first is a polynomial commitment scheme that can efficiently commit to bits without embedding overhead. So we can commit to the individual bits of a system that we want to use. We can very efficiently prove the bitwise AND relation. So and we can also prove XOR very easily because that's native in binary fields. And the way we prove bitwise AND is using an idea called the univariate skip and sort of optimizing specifically for that use case. We also have a special integer multiplication accelerator, which is a GKR circuit. So we have a specific technique for doing an integer multiplication check sort of in the exponent of our finite field using a GKR circuit. And the last kind of unique thing about this system is word-level wiring. So instead of having wiring information per bit, we group all the bits into 64-bit words and do the wiring that way. And that is very natural for programs which are, a lot of hash functions are based on 32 or 64-bit words. I will mention that this is not a VM. This is not capable of proving Ethereum blocks. This is for simpler client-side use cases, and it's in a circuit model. So this is the one picture diagram of how things work. So we have a witness on the left, and for every witness word, which is 64 bits, we get to apply some bit shifts. We can XOR accumulate as many bit-shifted things together as we want, and then we can either apply or constrain them with bitwise AND relation or the integer multiplication relation. And this is only a few tools, but it's really powerful and lets us prove a lot of hash functions. It lets us prove we've written circuits for elliptic curve signing. We can do Ethereum signature verification using the mole constraints. And our performance numbers are really good on the CPU compared to Stu and Plonky 3. Our single-threaded and multi-threaded performance for hash functions are the best that we benchmarked against. So the point I'm trying to make here is with just a few primitives that are sort of carefully distilled out of the research that we did with Binius, optimizing specifically for bitwise relations, we can have this very powerful prover model, and it's working for client-side proving. Now, as I said, this is not a VM, but these techniques, I think, could be adapted really well to the VM setting. And in fact, our bottleneck with this system is one that was surprising to us, which is the wiring argument. And I think that could be optimized away in a VM context. I want to, aside from the cryptography here, make one final point about simplicity. So we're building systems and technologies to secure global financial infrastructure. And there's been this explosion of ideas in the space. And this process of building Binius v0 and then Binius64 has really enforced not just the importance of simplicity to me, but that simplicity requires sacrifice. But it's worth it because the complexity of these systems compounds. And if that was my experience with this, so thank you very much.
OK, thanks, Jim. I've got a couple of questions here. First question. Any future plans, roadmap for Binius64 that you have in mind?
Definitely. So Binius64 is not zero knowledge yet. That is on the roadmap, intended to get it done within a few months, and then it will be a zero knowledge proof with proof sizes on the order of 100 couple kilobytes, and then beyond that, the roadmap's unclear.
Is the wiring verifier linear? If so, how how do you plan to address this?
Is the wiring verifier linear? The verifier is, I mean, it will be a succinct argument with, sorry. The wiring verifier right now it needs to do a matrix evaluation, so it is not succinct, but it can be made succinct using the standard Spark technique that's in Spartan. So it would be a sublinear verifier for wiring once we go and implement that.
And then personal question, well, from me, not a personal question, but have you checked out the new client-side proving dashboard on ETH proofs that just launched?
Someone sent me a screenshot of it.
Yeah,
that needs to go.
Binius64 is atop several leaderboards. So
Cool.
Interested to see if you have feedback on it. If you do, I'd love to put you in contact with the team.
Absolutely. Thank you.
All right. Thank you very much. Up next, we got Leo Alt from Powder talking about auto precompiles.